Hello, everyone that has joined so far. Hopefully you can hear me. And hopefully you can see the slideshow. Yep, hi, Shelly. I know it says 6 p.m. on this slide, but I chose this time of 3 p.m. True. At least there's that. It is 6 p.m. somewhere in the world. Still someone joining. Once it hits 3:02. So I guess I'll start right now. So yeah, welcome everyone to the first review session for college algebra this summer. I did not make these slides. Disclaimer, I'm just presenting them, so hopefully the review questions will be nice and instructive. How do I go to the next slide, Kim? Yeah, so these will be the topics we'll be doing, where we simplify algebraic expressions. Polynomials are very common. And radicals like square roots is another word for that. We factor expressions, and most importantly, solving, because we have unknown variables in these expressions. Yeah, that goes without saying. Yeah, this is being recorded, by the way. Yeah. As someone else has done already, you can interact with the Zoom chat or the Q&A, actually. There's two of those things. So first, I believe we'll be doing simplification. Or actually identifying features of polynomials. So if I can write annotate. Okay. So first, or wait, did I just go to the next slide, or I go to the previous one? How do I go to the previous one? Why can't I assume it goes to the previous? That is what I'm trying. For some reason, it's not working this time. Oh, wait, now it's working this time. Okay. I thought I tried to left there already. Okay, now we need to get these chat boxes out of the way. Hopefully once I go to annotate, it doesn't go to next slide. Okay. Yes, first we got to determine the degree and leading coefficient of polynomial expressions. So the degree is just you look at all the exponents of the variable x in this case, like this is implicitly x to the first. This 5 basically has like an x to the 0 power. It's like the highest of these exponents is the 3 of the x. So that's the degree of this polynomial. And the leading coefficient is identify the coefficient before the x of the greatest exponent. So the 20. So I guess to record these answers, the degree is 3 and the leading coefficient is 20. And same dealio with part B. X to the 6 is the highest here because there's 2, and then I like to put x to the 0 right by the constant to remind myself. The highest degree is 6. Be sure to account for this negative sign in the leading coefficient. So it'll be -8 for leading coefficient, 6 degree. Then in this longer expression, this is x to the first, x to the fourth is higher. Now 12 is the highest one, 3 is lower, and 10 is lower. So the highest we encounter is 12. And even though it looks like there's no coefficient in front of the x, it's basically a 1 there, because multiplying by 1 does nothing. So the degree of 12 and the coefficient of 1. The arrows do the job. I think every time I have to stop annotating mode to go to the next slide. Okay. So clear what I've done so far. So the next one is simplification. Where basically we just make the expression more readable to humans. It's like all we're doing here. For the first one, we're multiplying two different expressions. So first, like let's multiply the constants 7 and 8. Well, that's going to be 56. And then x to the second times x to the third. When we're multiplying terms of the same base x and they have exponents, we add the exponents when we multiply them. So like this is just x to 2 plus 3 essentially is what's happening here. So x to the 5th. I can write that better. Then with the y is y to the 3rd plus 3 is y to the 7th. Sometimes my tablet does stuff. And then that's all we can do to simplify, like, what's the word for it? I'm not good at my English vocab today. I'm like, where I was thinking of there. Like it's the most, like it just requires the least amount of writing basically is what we mean by simplify. Like it's better to write as one whole coherent expression rather than two separate. So then for part B now, here we're dividing by things. So when we do that, we subtract exponents is the rule then. So like x to the 8th over x to the 5th. You subtract the exponents like this, 8 minus 5. So like that becomes x to the 3. And then we have y to the 3rd over y to the 10th. Now, I mean, it's just a personal preference for me that I just like to leave everything in the numerator, even if it requires a negative exponent. I'm not sure if your course doesn't like negative exponents. I'll just keep the exponent positive in this case. It's like y to the third minus 10 gets y to the negative 7. But we can make the exponent positive in the denominator. So I'll keep y to the 7th down here. Then it's just z over z. So those just basically cancel each other. And that's all for that one. Part C, 20 over 7 is conveniently 4. Then subtracting exponents again for the x's, x to the 5 over x to the 8. All right, as a fraction, 4 over x to the third stays on the bottom. And y to the fourth over y to the third. A y to the first remains on the top. I'll just put the 1 there for emphasis. And then part D is a slightly different situation. We have a whole expression raised to some power. So in that situation, then we distribute the 4 to each term. So first we have negative 8 to the 4th. I'll just write the expression like this first. And when we have x to the third and then raised to like the 4th like this, we multiply the exponents essentially. So 3 times 4 is 12, so x to the 12. Then y to the 7th times 4. You get y to the 28th. And then negative 8 to the 4. If I can do mental math. So like 8. You know, it'll be a positive number because the exponent is even. So that's good to know. And the way I do this in my head is I convert 8 to the 4th to 64 to the 2nd. But then what is that number actually? Actually, it's the same thing as 2 to the 12, if I remember my powers of 2. Is it 4096 if I remember? Just being sure I'm not doing this wrong. Yeah, 4096. If we wanted to convert the 2 to 12 into its actual number. So in the end, we get that. Lastly, part E, where there's going to be many more steps to this one than the previous ones. So first of all, we might as well distribute this 4y into these parentheses, the terms in the parentheses. So 12 is 4 times 3, xy, and plus 24, y times y squared is y cubed. And then we keep the 4xy squared, and this is all over xy. So we notice there's an xy in this term. There is an xy in this term. There is an xy in the 24y cubed, unfortunately. Well, at the very least, we can get rid of y from each term. These chat boxes are in the way. So 12xy over xy, the 12 just stays. And then 24, we can remove one y from y cubed because we're dividing by y, but then the x remains. I'm not sure if we can simplify even more than this, then plus 4y. Technically, we could factor out a 4 out of every term, but what does that really do? I think it's fine to just end up like this. Like there's no way to further combine terms really. Okay, so that's all for that part. Okay, now we have square roots, which might be slightly harder to understand than just polynomials. It's like the square root, basically. I mean, it's the same thing as like raising whatever's inside the square root to the 1/2 power. If that reminds you what square roots do. And I guess the way we quote simplify this is that we find perfect squares, or like we factor the number inside and find perfect squares. It's like 45. We can turn it into 5 times 9. Conveniently, the 9 is a perfect square. So like what happens basically, that we can turn this into the square root of 5 times 9, but the 9 is the same thing as 3 squared. It's like the square root of 3 squared. We can just take a 3 out in front of the square root and just leave over the 5 inside. So that's how we simplify these radicals. They're called square roots. But then here we're adding 2 different square roots. The key thing is that we can combine them if the inside of the square root is the same. So like again, we need to like factor these numbers and try to get something common inside both of these square roots. So 50, there's not much to do. I mean, there's 2 times 25, and there's like different options. There's 10 times 5. It's also 4. Is that all we can do actually? Then the 32 is just 2 to the 5th, really. It's like the best we can do really is 2 times 16 to try to get a 2 in here and this 2 in the square root. And conveniently, this 25 and 16 are perfect squares. So this becomes square root of 2 times 25 plus square root of 2 times 16. And the 25 is 5 squared. So the 5 comes out in the beginning. And then 16 is 4 squared. So the 4 comes out of the square root. And yay, we can add these together because square root is in both terms. It's like you basically can factor square root. You just add the 5 plus 4. So it just becomes 9 square root of 2. And then part C, once again, for the 72, think of how far we can factor it with getting perfect squares. So like 8 times 9 came first to me, but I can split this 8 further into 4 times 2. And the 9 is still there. Well, 9 times 4 is 36, which is the biggest perfect square we can have. So the 2 is just left over. Then n to the 7th, the square root is just the 1/2 power. It's like the square root of n to the 7th. You can just convert into n to the 7 over 2. So in the end, we simplify this as 72 becomes 2 times 36 n to the 7. So I'll just take the 6 out and then the n to the 7 over 2 out. Should I do that? Oh, I don't know. Yeah. I did see the raise a hand. I believe I do Q&A at the very end, or you can just type in the chat if you think I did something wrong, or maybe it's best to keep the n to the 7 and the square root. Maybe that looks better aesthetically. Either way, maybe it suffices. So that's all for the radicals. So now we're like doing the opposite of simplifying in a way. We're going to distribute and add things together. Because it's not easy to tell this is a polynomial in this form, but when we distribute everything, it will be easy to see. So 3x into this, and the 6 into this. So 3x times 4x is 12x squared. 3x times negative 5y, negative 15xy. And then 6 times 2x squared is 12x squared. Negative 8y times 6 is minus 48y. Yeah, so conveniently, we can combine the 12x squared and both 12x squareds. Wherever maybe these slides, part B should be down here, so I can write more. I'll just write up here, this will be equal to, you can find the 12x squared to 24x squared. And we just keep the minus 15xy minus 48y. And so the term foiling was made for something like part B, where we have two terms multiplying each other, and both terms have two terms themselves. So the F stands for first. I mean, you don't have to remember FOIL exactly. I mean, how I remember is that every term gets distributed into every term of the next expression. So like this 5a has to be distributed to the 2a and 4b, and then the minus 3b is distributed to both of those terms as well. I noticed people raise their hand. Oh, I didn't scroll down far enough. It's okay. So back in the square root of n to the 7th. I mean, the n to the 7th was just n the square root to begin with. I'll read all the Q&A when I'm done with my review parts. answer those questions at the end, just so oopsie, previous. So when we quote FOIL this out, 5a times 2a is 10a squared, and 5a times 4b, 20ab. Negative 3b times 2a minus 6ab, and negative 3b times 4b minus 12b squared. And we can combine the like terms that have ab. So 10a squared plus 14ab minus 12b squared. I mean, I'm not sure what to do about raising hands, whoever is doing it. I mean, you can type in chat. Q&A is meant for the end though, so let's continue going. So now for part C, now there's 3 terms in this. So there's gonna be a lot more distributing going on. First, the 4c squared in all 3 terms. So for 8c to the 4, minus 20c squared d, and then 12c squared. And then the minus 6d in every term, minus 12c squared d plus 30d squared minus 18d. So can we simplify? I'm pretty sure we can. Yeah, we have terms involving c squared d minus 32 c squared d. That's pretty much all we can simplify. Every term has different variables and exponents. Yeah, so expanding just means we put it into a form like this where there's no like multiplying of terms like this. We expand them out so there's only addition, subtraction between them. And now factoring. Factoring is a pretty convenient is a convenient tool, especially when we say put this equal to 0, and then we do a product of factors like equals 0. It's like typically how we solve many different things. So for the first one, we're essentially just finding terms common, or we're finding like what's common to both of these terms in this expression. So 14 and 42, the greatest common factor between those will just be the 14, because 42 is 42 times 3. The next to the q next to the 5th, x to the q is the greatest, or the GCF, I'll just say. And y squared can be factored out of both of those. And so then what's left? Well, we factor out a 14, so nothing is left there. We also did x cubed, so nothing's left there. Only y squared remains there. 42 was split into 14 times 3, so a 3 remains there. Then an x squared remains from x to the fifth. And then the y squared was factored. So that's all for that part. And now we have a cubic polynomial for part B. And if I remember, factor by grouping is really all that we can do here. Yeah, factor by grouping. And essentially how we do that is that we put the n cubed and n squared terms right beside each other, then the 8n and the 4 separate by now. And we try to factor them such that we get a common expression in like the parentheses that end up happening. So if we do 3n squared here, because that's how we would factor this, like 2n plus 1 remains here. Like, can we get 2n plus 1 like here as well? Like, can we factor something out such that we get 2n plus 1? And like, luckily we can. Because if we factor out a 4, just 2n plus 1 remains there. And so the way we combine these is that we factor out 2n plus 1 out of both of these things. So then the 3n squared plus 4 is common to both. So that's how we would factor that one. There isn't really too much space. Part C right here then. So when we just have what's called like a quadratic trinomial like this, we ask ourselves numbers that add up to 14, or I mean, multiply to 14. And numbers that add up to -9. Yeah. So like when we factor out 14, there's really only plus and -2 and plus or -7, because we need to get to positive 14. We could multiply by negatives or positive. But since this 9 is negative, we would choose -2 and -7 from this. So now that we know those numbers, it just becomes two terms where it's x plus the first one times x minus 4 plus the -7. That's how we factor this. Because if you were to expand this, you would get x squared minus 7x minus 2x plus 14. So we know that this does work indeed. Part D is slightly trickier because now there's a 5 in front of the x squared. So in this situation, now we want numbers that add, or I mean that together they multiply to 6 times 5, 30. So numbers that like multiply to 6 times 5 is 30. And then they add to 13 as well. So 30, I mean, there's 6 times 5 like that. That doesn't add to 13. But there's 10 times 3 that we can do. Oh, that adds up to 13. So we would choose those. But obviously we can't just put x and x like this because there's a 5 in front of the x squared. So I believe, I mean, I'm not sure the exact way you were taught this. But I believe what happens is that we split the 13x into 10x and 3x like this. And it's like we try to do the factor by grouping again that we did in part B. It's like for the 5x squared plus 10x, we can factor 5x out of both of those. X plus 2. And can we get an x plus 2 from this? Luckily we can when we factor out a 3 from it. And we combine them just like we did in part B, where x plus 2 multiplies both the 5x and 3. So we just add 5x and 3 together right here. And that's how part D would be factored. Background noise. I forgot how much I had to do. So back to simplifying, interestingly. But the way we simplify these will involve factoring, though, is the difference between what we did previously. So like the only thing we can factor here is the top. And just like we did previously, numbers that multiply to 6, well, there's plus and minus 2 and 3. -2 and -3 would add to -5. So you can turn this into x minus 2 times x minus 3 over x minus 3, and woo, we have x minus 3 over x minus 3. So only x minus 2 remains. Oh, part B, though, looks a lot more complicated. How would I approach this first? So first I would notice, let's just first factor out the 2x squared plus 10x. We can only factor out 2x out of that. So there's an x plus 5. Now let's try to factor out the x squared plus 2x minus 15. Maybe it contains an x plus 5 as well. So numbers then multiply to -15 and add to 2. I mean, you would get plus or minus 5 and minus plus 3. Because the numbers have to be opposite sides to multiply to -15. So like we would choose +5 and -3. And that's pretty nice. And x plus 5 we get out of this factoring. So to reorganize all this, well, first I'm just going to how should I write it? I'll just first write it like this. Maybe this is easier to read. Because when we multiply fractions, we just multiply their tops and bottoms together. So before I actually apply these factorizations, I'll just note that we can remove an x from the top and bottom. Like we can turn the, how do I write this down? It's like, because we can get rid of this x squared, and like this x. Because like x squared minus 9x would be x times x minus 9. And this 8x squared is like x times 8x. So really what I did is I got rid of these and these x's right here. And then I'll also apply the factorizations that I got up there. 8x times x plus 5, x minus 3. And 2x, x plus 5, x minus 9 remains. So x plus 5 disappears from the top and bottom. And then 8x over 2x is just 4 on the top. So that's all that we can do, actually. Yeah, that's as far as we can go to simplify that expression. So here we have a division symbol. So we can just rewrite this with multiplying the reciprocal of the second term. I'll just rewrite this as times x squared minus 2x over x minus 5. And then we can proceed to factor many things here, like these and that terms. So for the x squared minus 3x minus 10, numbers and ones points in -10, -5, and +2. Also happens out to -3. And then the x squared minus 4x plus 2. Is there anything we can do there, actually? I'm not sure if we can. Yeah, there's actually nothing that can be done there to factor out this. Because, like, if you find numbers that multiply to 2, like there's really only 2 and 1, but we can't get as high as -4 or -2 and -1. Like that only goes up to -3, not -4. So not much really can be done there, actually. So the x squared minus 2x minus 10, I don't know, x minus 5 and x plus 3. We can only keep x squared minus 4x plus 2. And then the x squared minus 2x, there's a x common in both. That doesn't really help too much. Oh wait, I forgot I did the reciprocal. Yeah, I may have written something. X plus 2. Oh yeah, true. Yeah, everyone does make mistakes, huh? Yeah, no matter how much I practice, I do this. Or did I? Oh yeah, this should be x plus 2. I don't know where 3 came into my brain. Okay. Yeah, x plus 2. And I should remember I did the reciprocal. I was about to. Yeah. And I did say it because I don't know, things just pop into my mind. I don't know. So I had it as x squared minus 2x over x minus 5 after I did the reciprocal. So this x times x minus 2 should be up here. Yeah, I think this should be good. Yeah, all we can do is just get rid of this x of these x minus 5s. And just a little note, we can put x plus 2 times x minus 2 as x squared minus 4. If you remember, like the difference of squares, if you've done that before. So I'll put as x times x squared minus 4. I don't think there's any magical cancellations you can do from here. Because this looks like an x squared minus 4, but not really. So I don't think anything can be done from here. So that's all for this part. How much more is left? Oh yeah, and then finally we're solving. I think this is the last section if I remember. Yeah, it all led up to this point of finally solving for unknowns. So for part A, well, fractions, they say, do be annoying. But we can get rid of this complex fraction on the right by essentially multiplying everything by 2/7, like the reciprocal of 7/2. So like this becomes 3/4 times 2/7. It becomes like 6/28. And then 7/2 and 2/7 just disappear. That's why we did it. Now there's more fractions, but what is the least common denominator of all of these? It's probably a big number, isn't it? Is there anything better to do than find least common numbers? Well, this 6/28 is actually really 3/14. If we were to find least common denominator, it would have to be 7 times 5 times like 6. That's 210 right there. Or actually, even more than that, actually. It had to be 7 times 5 times 12 if we wanted a common denominator. Well, that's pretty huge, though. But why not do it? Because then we get rid of the fractions that way. So 420 divided by 28 is 15. So like this will become 15 times 6/420. Then 420 divided by 5. This will become 84 times 2/420. And 420 divided by 24. I mean, that still doesn't even get the least common denominator. Because this gets 17.5 up here. Oh, well, I committed to this route. It'll have to be. So everything's like over 420 basically. So we just get rid of that. So like all that's left is 15 times 6, 90. 84 times 2, 168. X plus 17.5. No one has called me out yet on a mistake. That's good. 90 minus, so X is just 90 minus 17.5 over 168. Whatever this becomes. I just realized it's 350. Oh no, I'm going slow today. I mean, I'll just keep it as 72.5 over 168. It's like, it's gonna be a decimal that it'll be simplified to. I should have done this quicker. Okay, so for this one, we multiply everything by 9 times 6x minus 8 to get rid of the fractions. 45 equals 8 times. You distribute the 8. You add 64, 109. And solving for x here, there is an extra y, but we don't care that y is an unknown here because pretend it's not there. So like solving for y means we just isolate x. So like we can put everything that isn't that, or everything that doesn't have x on the right side of the equation. So we'll have 5x equals, we'll add 8y over, subtract it. 15 minus the 8y, and then plus 6 when we add that over. So x is just 15 plus 6, 21 over 5. So that's how we quote solve or isolate y, or x. Now this one, we would multiply both sides by 2 plus x. Distributing. So again, add everything to the other side that isn't x. Subtract 6y over 1 minus 5y. And just divide by 3y. So the x is just left over. And finally, this one, we can factor out an x out of both of these terms. It's the key thing to recognize. So we just divide like the 5y plus 3y squared over. Hopefully that made sense when I was speeding up. Is this all actually? Yeah, that is all. Okay, so I did finish in time. Yeah, so now Q&A is open. But yeah, just to know about our resources. We are always inventing new technologies. So we have a tutor bot that can possibly help with this, I believe. Yeah, because Mat 117 is included right here, also in this online study community. And I'm one of the tutors in the online tutoring center. I should have said in the beginning. Is that the last slide? Okay, but yeah, I can go, if the anonymous attendee is still here, I can go back to the square root of n to the 7. But yeah, that was just my choice to do that. Like square root of n to the 7, you can write it as this. Because like anything in a square root is the same thing as raising the input of the square root to the 1/2 power. So like that's why square root of n to the 7th, I just put it as n to the 7th, like over 2. Either way will suffice though. Yeah, thanks all for coming. I noticed people have just been leaving. Admittedly, in hindsight, I went pretty slow today because I'm like, yeah, there's only literally 5 minutes left. And yeah, this is recorded, so don't worry if you missed a lot that I wrote. Yeah, like since we do like review sessions every hour, I kind of realized too I was approaching the end of this session. Yeah, but I'll have to like end it now, like just in case someone else is going to review at 4 p.m. for a different class. Yeah, so Julia and Ryan, I'm gonna end the session.